Starting today's lecture onwards and in the next 2-3 lectures, I am going to talk about the various applications of fractional in fractional calculus. So, in today's lecture I am going to talk about an applications of fractional calculus in ODEs and later on in integral equations. Especially in today's lecture I am going to highlight some special integral equations, namely the Abel's integral equation. Now, just want to highlight Henrik Abel was a Norwegian mathematician who among his various other contributions have greatly contributed to the development of fractional calculus. So, today in this lecture I am going to highlight some of his contributions in solving these integral equations. So, let me just recap what we did from the last lecture onwards. So, just to recap, in the last lecture I had introduced fractional calculus and mainly I had introduced three major results. So, the first result was the Lacroix formula of fractional derivative. So, according to the Lacroix formula, we have that the derivative, the fractional derivative of let us say a polynomial or a variable to the power exponent is given to be this particular expression. So, gamma of beta plus 1 divided by gamma of beta minus alpha plus 1 times x to the power beta minus alpha. So, the other result that we had shown was the development of the Riemann-Liouville's integral formula. So, according to the Riemann-Liouville integral formula, so Riemann-Liouville integral operator. So, according to this formula we have that if we were to evaluate the fractional integral of the function f, let us say of fractional order alpha, and the integration limit starts from let us say 0, well the general case is a, then we have that this fractional operator is equivalent to this following integral. So, this is 1 by gamma of alpha divide times integral from a to x t minus x to the power alpha minus 1 f of x dx. Okay. So, wherever we are going to encounter in today's lecture, we are going to encounter this integral operator that is equivalent to this particular integral formula. Okay. So, the third result that we had highlighted in my last lecture was how to find the solution or how to integrate these fractional order integral equations. Okay. So, typically we use the method of Laplace transform. So, what we had said earlier was if we were to evaluate fractional integrals. So, to evaluate fractional integrals, I will be using the inverse Laplace transform method, and that is the way. So, suppose we are given the fractional integral that we have to evaluate, we will take the Laplace transform, and we have shown that this is nothing but the convolution of the Laplace transform of the convolution of two functions. The first convolution, the first function g is nothing but this operator. So, the function corresponding to this operator, and of course, the second function is corresponding to this function f, and that is given by this following result. This is also equal to f of f bar of s, and then the next step is, so let me call this a, the next step is to find the inverse Laplace transform, of let us say this expression of 1. Okay. So, going via the Laplace transform method is a natural choice to solve these fractional integral equations. Okay. So, today I am going to start my lecture by introducing fractional ODEs. So, let me just consider the most general form of fractional ODEs. Okay, so let me just further simplify this topic by saying that my coefficients in the ODEs are constant coefficient with constant coefficients. Okay. So then let me say that an ODEs are going to be a fractional order ODE. Let me show you the most general expression. Let me say that this is of order n with each fractional derivative as d alpha. Let me have that the coefficients of these derivatives are ai's. So the operator is as follows. So let me write the most general operator. So this is an operator. Let me call this operator as f of d. This operates, let us say, on the function, and we want to evaluate this function, and let me just introduce the ODE which is the homogeneous ODE, and further let me assume that my variable t is non-negative. Okay, so then let me just say that my fraction alpha is 1 over q, and let me further assume that q is, well, q is an integer. Okay. So q is an integer. Okay, so then let me just highlight one particular example. So let me call this as example 0. So if I were to say that q is 1, that is, alpha is not a fraction, but alpha is an integer, and let us say n is 1. So then what I have is n is 1 and alpha is 1. So then I have a first order ODE. Okay. So let me call this expression 1. So first order ODE from my expression 1. Okay. So that is the regular ODE that we have. So which means that for alpha taking non-integral values, then we will have a fractional ODE. So let me just give you one example in how to solve that particular example. Okay. So the example says, consider, so now whenever I am going to look at an ODE, I am going to talk about the ODE of the form n comma q. Okay. So when I say ODEs of the form, let us say consider an ODE of order 2 comma 2. So this means that my n is 2 and my q is also 2. So rather than defining, so in a regular ODE we have just one value which denotes the order of the ODE. In a fractional ODE we have two values denoted by n and q, which denotes the order of the ODE. So then for a fractional order ODE of order 2 comma 2, then my f of, in this case, d alpha is half, which is 1 over 1 by q. So d alpha of x of t will be as follows. We see that this is also, notice that if I plug n equal to 2 and alpha equal to 1 by 2, my highest order is d of 1, and then my next order we will see that, so let me call this as, so this is a1, so d n minus 1, so that is 1 times 1 by 2. So I get the next derivative order as d half, and then the third derivative is d to the power 0. So that is not a derivative at all. So then evaluated over the operator evaluated over x of t, this is equal to 0. So so as I just highlighted, the way to solve this ODE is that I am going to apply Laplace transform on this ODE and then simplify and then invert the transform to get back the solution. Okay, so what I do is apply Laplace transform. Okay, so Laplace transform with respect to the way, let me say the Laplace variable is my variable s. So in that case, if I were to apply the Laplace transform, so on the first operator the Laplace transform is quite straightforward. So d of x of t, so I have d of x of t, then the second one is a1 times Laplace transform of d of half of x, and then the third one is a0 Laplace transform of d0 of x, which is x itself. and then that is also equal to Laplace transform of 0, which is 0. Okay, so as I said, the first one is quite straightforward. This is nothing but s times, let us say the Laplace transform of small x is capital X minus the initial condition. So, the initial condition, let me denote it by x of 0, and now the second one we will be using my integral operator form. So, I know that this quantity d, the d half of x, which is the derivative operator, can be written as d negative half of d of x, okay, plus the rest I can write. But notice now, this is d half of x is d negative half of d of x, that is one and the same thing. So, we have broken down one operator into the composition of two equivalent operators here. So, let us continue this. Let us look at this special, this second term in this equation to see what happens. So, what I have is the following. So, this is s times x of s minus x 0. So, that is my first term. Now, in the second term, the operator was d to the power negative half. So, that brings in, with my Laplace transform method, that brings in a factor of s to the power negative half, and then the Laplace transform of d of x, right, and plus a 0 Laplace transform of x, which is capital X, and that is set to 0 on the right hand side. Now, notice that this can again be evaluated further, and this is going to be s times x of s minus x 0. Okay. Now, notice that there is a multiplication of s to the power minus half outside. So, we are going to distribute this factor into this coefficient. Okay. So, then what I see is this is x bar minus x 0 plus a 1 times, let us distribute s to the power negative half, I get s to the power half x bar minus s to the power negative half x 0 plus a 0 of x bar, set it equal to 0. So, let me just simplify all this. Let us bring all the coefficients of this capital X of s, which is the Laplace transform of the solution, in on one side, and we see that the following expression emerges. So, I get s plus a 1 square root s plus a 0 x of s, and that is equated to x of 0, that is my initial condition, plus a 1 d of negative half of x 0. Well, we see that this was the initial condition. So, I must have kept it as the operator itself. So, because that this is a value, this is not, this particular quantity is not a function. Okay. So, then let me just simplify further to come to this expression x of 0 plus a 1 d to the power negative half x of 0, and then in the denominator I have the following factor. Now, notice, let me call the numerator as a. So, why? Because notice that the numerator is just a constant, the denominator is purely a function of s. Let me call this as f of, so it is a function of square root s. So, f of s. Okay. So, then let me rewrite this expression as follows. So, this is a times 1 by square root s minus a minus square root s minus b. So, what I have done is I have used my method of partial fractions to break this denominator into two simpler partial fractions given by the following. Now, of course, if we were to equate the partial fractions equivalent to this denominator, I get back this coefficient as well. Okay. So, then notice that I am going to continue to simplify this expression. I have that this partial fraction can be written further as square root s divided by s minus a square plus a divided by s minus a square. So, well, just before moving ahead, I just want to highlight that a and b are to be evaluated. Okay, so evaluate. So I leave this as an exercise to the students to evaluate these coefficients a and b such that the product of these two factors square root s minus a times the square root s minus b must be equivalent to this denominator. Okay. So then let us continue simplification. So I get that from 2 factors I have the following 4 factors minus s minus b square. Now the reason I have reduced it into 4 simpler factors is because I am going to recall another result from my previous lecture. I saw that the Laplace inverse of this following function 1 by s to the power alpha of s minus a is given by this e function e of t comma alpha comma a, and that is equal to this integral 1 by gamma of alpha integral from 0 to t zeta of alpha minus 1 times e to the power a times t minus zeta, okay, and that is d zeta. Okay. So, I am going to use this particular result to come and arrive at the inverse transform of this expression. Okay. So, we see that 1 by, so a by a minus b. So, let me just recall this expression again, s minus s square root s by s minus a square plus a by s minus a square minus square root s by s minus b square minus s minus b square. So, using my result that I just highlighted, I can immediately find the inverse transform and hence the solution as follows. So, this is e of t comma negative half of a. Students are requested to check that these according to these coefficients I get back the Laplace inverse for these factors. So, then this is also equal to the second one is e of t comma 0 comma a square, and then the second one is e of t comma negative half comma b square, and the fourth one is negative b times e of t comma 0 comma b square. Okay. So, then we have seen one method on how to calculate, on how to evaluate this ODE. So, we can evaluate ODEs of general order n comma q in a similar fashion. So, let me, before I move ahead to the integral equations, let me just highlight another topic, that is the topic about the existence of the solution. Okay. So, I am going to talk briefly about the conditions of on the existence of the solutions that we have just evaluated. Okay. So, when is it possible that we can evaluate the solutions to the ODE and when it is not possible. So, conditions for existence and causality of global solutions, okay, of fractional ODEs. Okay. So, I am briefly going to talk about the existence criteria. So, let me just consider a fractional ODE. So, consider the ODE of this form, which is given by, let me call this as my operator f of d, which is operating on this solution x of t, which is also equal to f of t. Okay. Let us say I am further given initial and boundary conditions. Let me say that t is a real number, and then my operator is as follows. My operator is, let me say this is d to the power alpha n plus a n minus 1, where alpha n is n times alpha, okay, plus a n minus 1 d to the power alpha n minus 1 plus and so on, plus a 1 times d to the power alpha 1 plus a 0. So, that is my operator, the ODE operator, where my d is the derivative with respect to t, the variable t, and of course, I have the following order in my fraction coefficient, and further I assume that ai's, the coefficient of these operators, they are all real. Okay, so, real coefficients. Okay, so, then I know in order to solve let me call this as 2. In order to solve 2, I have that 2 is equivalent to x of t equals f d inverse. So, I am assuming that I can take the appropriate inverse of the operator which is applied on the right hand side f of t. Now, if I were to use the method of Laplace transform, take a transform and then apply the inverse, I am going to get that the solution is nothing but the convolution of two functions. Let me denote it by g convolved with f of t. Okay, so, then in terms of the convolution definition, this is also equal to this infinite integral of g tau f of t minus tau d tau, okay, where the convolution, in this convolution the function g corresponds to the functional equivalent of this operator f t inverse. Okay, so, then let me just rewrite this convolution further. So, what I have is that this convolution is integral negative infinity to infinity f of t minus tau g tau d tau. Okay. So, now what I do is I am going to apply my Fourier transform. So, apply, let me call this as 1, apply Fourier transform to 1, and I see that my, well, I can always rewrite this function g of t as integral. So, let me just rewrite this function in terms of its Fourier coefficient. So, which means I can rewrite this integral as follows: f of t minus tau integral e to the power I omega tau d tau, and let me call this the Fourier, the transformed function of g of t as 1 by tilde p of omega. Okay. So, what I have done is my Fourier transform of g is given by 1 by p tilde. Okay. So, g is nothing but the inverse transform of this function, which is given by this integral from negative infinity to infinity, and of course, I have a factor of 1 by square root 2 pi. Okay. And then let me pull this d tau here, and this is an integral with respect to the Fourier variable omega. Okay. So, then what I mean to say is the following. So, g of t is the following function in the transformed plane. So, this is e to the power I omega t p tilde of omega d omega, okay, where omega is the wave number in, and it is a real number. Now, why I brought up this particular expression, this particular representation of g is that notice my factor p tilde of omega. So, let me write down this coefficient, this factor p of p tilde. Now, notice that g in the physical plane is the operator equivalent, which means I can write down in the Fourier plane, p tilde will have the corresponding factors I of omega for each of the operators. So, my p tilde will look as follows. So, this will be I of omega to the power alpha n plus a n minus 1 I of omega to the power alpha n minus 1. So, we see that in the physical plane g was the operator. So, we had the derivative operator of order alpha n, order alpha n minus 1, and so on. In the transformed plane, this is a polynomial of order alpha n, but the transformed variables are I omega. I see that if I continue, I get the following polynomial. Now, notice that this solution, I need that. So, this was my solution x of t. So, my solution x of t is nothing but the convolution of these two functions, which means that if the convolution has to exist, it is only possible if the solution to this particular polynomial set equal to 0 exists. Okay. So, what I just said is the following. What I said is the existence criteria for my ODEs, my fractional ODEs is as follows. The solution to 1, the 1 is this given expression on top, exists if 1 by p tilde omega, which is the transformed equivalent of this operator, is first of all square integrable, it must be square integrable, and secondly, if I were to look at this following polynomial, well, consider this following polynomial. Let me call this as q bar of s. This is nothing but p tilde of I of s, which is also s to the power alpha n plus a n minus 1 s to the power alpha n minus 1 and so on, plus a 0. I see that this has, provided that if this particular polynomial has stable solutions, then this is only possible if and only if. So, this particular polynomial set equal to 0 has stable solutions if and only if I get that the roots, the real part of the roots of this polynomial q bar is less than 0. So, which means that if this criteria is satisfied, I have the stability of my solution, stability of the solution given by my expression 1 here, which means that my solution is going to asymptotically go to a finite value if this polynomial has roots whose real parts are less than 0. Okay. So, if that is the case, let me call this as my condition 3. So, if 3 is satisfied, what I get is, I can immediately say, let me say that Sk given to be these numbers, let me say that this is a complex numbers. So, Sk being the roots of q. So, Sk's are the roots of q. So, I have denoted the roots with a negative real part. So, what I have is sigma k's are positive. Okay. So, let me say that the roots are such that the real parts are negative, then in that case using my standard Cauchy's residue theorem, my Cauchy residue theorem, I can immediately find my operator equivalent g of t to be this following summation, which is of this form, e to the power negative sigma k of t cos omega k of t plus let us say epsilon k. Okay. So, which means that once I have negative roots, I can immediately evaluate the Cauchy's residue, the Cauchy's contour integral to come to these the contour integral at those following at the singularities which were the roots, and I get back this following integral. Let me say that there are infinite number of roots and all these roots are given by sigma k plus I omega k. So, we see that this is nothing but a phase shifted oscillatory function. Okay. So, phase shifted oscillatory function, and then further we will have some remainder terms. Let me call this as plus, well, this is with a minus 1 by pi integral 0 to infinity and e to the power negative r t divided by let us say q of r, okay, dr. So, what I see is that I call these as my relaxation my relaxation function, and they become dominant when the solution is far away from the initial condition. Okay. So, dominant when the solution is far away from the initial condition. Okay. So, briefly what I have highlighted is that my solution to the ODE will exist if my corresponding convolution exists, and the solution is finite if I have in the convolution I have those roots of the polynomial in the transformed plane had negative real parts, and in that case we had the following expression for the operator g of t. Okay. So, then